ladies and gentlemen, just to kind of recap what we did in the first part of this chapter, which is on the gas laws, we discussed the three, what I consider the three very basic gas laws. Boyle's law, Charles' law, Gay-Lussac's law. We put them all together into one big one, which we call the combined gas law. Okay? But if you'll notice, nowhere in this first part of chapter 5 that we have already covered, nowhere did we talk about amounts of gas. Okay? We never had a mass of a gas or moles of a gas. We didn't do any of that. If you start talking about amounts of a gas, then you have to use this equation, your ideal gas law. Okay? So, you've used this before. You used it in Chem 1. So, let's talk a little bit about these variables, and more specifically, let's talk units, because units are really important with this one. Okay? P is pressure, and you can have actually four different possible units for pressure. Most of the time your pressures are going to be in atmospheres, but you could also have pressures in kilopascals, torr, millimeters of mercury. Remember that torr and millimeters of mercury are essentially the same thing. Okay? V is volume, and ladies and gentlemen, your volume must be in liters. If you put a volume in milliliters, for example, into this equation, you will get a wrong answer. Okay? This lowercase n, that's moles of the gas. I'll come back and talk about R in just a second. T is temperature. It must be in Kelvin. Don't ever plug in a Celsius temperature. And guys, R is called your ideal gas constant. And there are actually three possible values that you could plug in for R. And how do you decide which one to use? Do you remember from Chem 1? How do you know which one to use? Josie? Correct. It depends on what your units of pressure are. Okay? So, for example, if you're given a pressure in atmospheres, this is the value for R that you would use. How do you know that? Because you see atmospheres as part of this unit. The other one that you're probably familiar with, if your pressure is in kilopascals, do you remember what the value for R is? 8.314. Very good memory. 8.314 is the value for R you would plug in. And then there's a new one that I don't think any of you have used before. If your units of pressure are in torr, or millimeters of mercury, which are the same, those are the same units of pressure, this is the value you use, 62.4. Now I have some wonderful news for you. Do you need to memorize these numbers? No. Do you know why you don't have to memorize them? Because I have not given this to you yet, but from now on every test and on the AP exam itself, you will have an equation / constant sheet. Okay? I'm going to make copies of this for you for next week. And all of these three values for R are listed right here. I know you don't have it in front of you. And how do you know which one goes with which? Because their units are written right next to it. Okay? Next to this one, you will see torr, so you know that that's the one to use. Okay? And I'm sure most of you can remember the ideal gas law, but in case you couldn't remember PV equals nRT, that's on your equation sheet also. Okay? So, here's the deal, guys. You think about what the word ideal means. It means like in a perfect world. Okay, no problems, no error, no anything like that. Well, gases in the real world are not ideal. Okay, they have abnormalities about them. So why do we use the ideal gas law if real gases don't behave in an ideal way? It's a pretty good approximation. I will show you at the end of this chapter what the ideal gas law would look like if you were going to take real life conditions into account. It's pretty complicated. For those of you that are either currently in physics or have taken physics, you know how you have to do a zillion problems where you're throwing a ball up in the air, or a cannon launches a cannonball. You know, these arc problems where you measure the angle and the velocity. Yes? You know what I'm talking about? There's always these throwing a ball in the air problems. Okay? Well, what you've probably maybe never thought about is that never have you had to take wind resistance into account, or air resistance. Okay? But in the real world, if you're trying to calculate something about a projectile kind of motion, you need to take that into account because it does have an effect. The reason that you don't is because the calculations for real world conditions are incredibly complicated. Okay? So you use what you have been. We're going to use the ideal gas law because it's a good enough approximation. Okay? Now, we are today, first thing we're going to do is bring together two concepts, gas laws and reaction stoichiometry. Some of you will have put these two things together back in your Chem 1 class, some of you will not. Okay? And here's the situation. Okay? First of all, remember that the word stoichiometry implies that we have a reaction taking place. Okay? It's not just converting grams of a gas to moles of a gas. No, we have an entire reactance going to products. You've balanced the equation. If you come across a problem like that in this gas laws chapter, the question you need to ask yourself is, am I at conditions of STP? STP stands for standard temperature and pressure, and these are the conditions for STP. You need to know that. 0 degrees Celsius, what is that temperature in Kelvin? 273, good. Pressure of 1 atm. If you are at conditions of STP, and you're given, let's say it's a problem where you were given a mass of the reactant, and the question says what volume of product will be made. Okay? If you are at STP, you may use the number 22.4 to do your conversions. Do you guys remember I gave you that little flow chart for stoichiometry problems that looks something like this? Do you remember that? Okay. If I was given, let's say, grams of reactant and I'm asked to go to liters of product, how many steps is this problem? 1, 2, 3. It's just train tracks, T-chart, whatever you want to call it, a 3-step conversion, and it is okay to use that number 22.4. Okay? What if you're not at STP? And I'm going to show you examples of each of this type in just a second. If you will notice, nowhere in this bullet here have I said anything about the ideal gas law. The only time you would need to use that is if you have a reaction that is not at STP. And you can't just use the ideal gas law. You'll have to use the ideal gas law along with some kind of T-chart stoichiometry conversion. Okay. So let's look at an example of each type. If you have the notes, the slides, there's something missing, and I apologize. There should be an AQ written after HCl. Just write it in if you have the slides. Apologize. Okay, I'm not going to do these problems for you, but I am going to just talk about them a little bit. Okay, so don't start crunching any numbers, just listen. The first one says, calculate the mass of sodium bicarbonate. Stop right there. Where is sodium bicarbonate? Reactant, product, what? It's the very first reactant. Please notice that it is not a gas. Okay? So calculate the mass of sodium bicarbonate necessary to produce 2.87 liters of something that is a gas, carbon dioxide, and we're at STP. We are at STP. Look at the previous slide. What is it okay to use? 22.4. Number 1 is a very Chem 1 kind of question. You don't need the ideal gas law. It's just a 3-step stoichiometry conversion. Let's look at the second one, however. This one is a little bit more complicated. I'm not going to do it for you, but I want you just to listen. It says if 27 liters of gas are produced, stop right there. What gas are we talking about? How'd you know it wasn't H2O gas? I mean, it says product. How come it's not NaCl? How did you know it was CO2? Because it's a gas. You have to pay attention to these things. Okay? So let's be more specific. 27 liters of CO2 are produced at 26 degrees Celsius, 745 torr. Does that sound like STP? No. What is the condition? What is standard pressure in torr? 760. Okay, so we're not at STP. Okay, great. Well, we're not at STP. Before I even read the rest of the problem, what do you know that I'm going to have to use? The ideal gas law. Okay. Well, do I have a pressure for this gas? Yes or no? Yep. Do I have a volume for the gas? Okay. Am I given a temperature? Yes. Do I know a value for R? Okay. So I'm ultimately solving for moles of what? Be careful. This is the ideal gas law. What gas are we talking about? CO2. Okay. You are given a second volume, but folks, that volume goes for HCl. I can't make this any more clear. You think this is so like basic? I would never make this mistake. I'm telling you, people make this mistake. HCl is not a gas. Don't you dare try to plug in a volume into the ideal gas law for something that's not a gas. Okay. All right, so this is where I know I'm going to start. Let's finish reading the problem. 2.6 liters of HCl are added. What is the concentration of HCl? Well, what's a concentration? What does that mean? Molarity. What do you need to find a molarity? Moles and the liters of HCl. Well, I have the liters. Okay, check. I don't have moles of HCl right now, but I have moles of one of the products. Can I get to moles of the reactant? Okay? Solve these problems. Go. Here's the gist, okay? If you have, and again, this is, you only even have to worry about this if there is a chemical reaction. Not all gas laws will have reactants and products, but these two both did. If your reaction is at STP, it's just stoichiometry and nothing else. And you may use the number 22.4 to get back and forth between liters and moles. If the problem is not at STP, you have to use the ideal gas law and some kind of stoichiometry. And folks, let me just clue you in that in this particular problem, we used the ideal gas law first, and then we did stoichiometry. It's not always in that order. You might, from the very beginning, be given grams of a reactant that's solid. Don't try to plug that into the ideal gas law. Do stoichiometry first to get into the moles of gas, and then you would use the ideal gas law. So it's not always in that order. Okay, now, when you are using the ideal gas law, you will sometimes see questions that bring in the concept of density and or molar mass into a gas kind of situation. And if you'll notice, nowhere so far have we said anything about density or molar mass. Okay? For any of you in this room that are really good at taking two different equations, substituting in one equation into the other, rearranging equations to solve for certain variables, if that is something you like, you're going to love this. If you don't like that, and you're not good at it, I have something for you too. Okay? Please tell me what this lowercase n represents. Okay, fine. Folks, if you see capital M anywhere in this chapter, it does not mean molarity. Sorry to say. Capital M does not mean molarity. It stands for molar mass. like masses you pull off the periodic table. Okay? Now I'm going to say something, and I don't want you to answer immediately. I just want you to sort of think about it for a second. You have a mass in grams, and you take that mass and divide it by a molar mass. What do you get? Moles. Just moles. Okay? Moles equal masses over molar masses. Well, I'm going to take this and substitute it in like that. Just rewriting the ideal gas law a little bit differently. It's the same quantities though. What is the formula for density? Okay. Well, if you look at our original ideal gas law, I've got the volume part, but mass is not in here. Mass is not one of my variables. Well, now it is. Can you all see how I could rearrange all these variables to get density on one side, m over v on one side? Okay. Yeah, multiply by big M, divide by RT, so it'd be PM over RT. Yeah, well, I'm actually going to even rearrange it further than that and write it like this. Okay? Molar mass equals density times the gas constant times temperature over pressure. And I'm going to share with you how my high school chemistry teacher got us to remember this. Molar mass equals dirty P. Ew, gross. You won't forget it. Molar mass equals dirty P. Ew. Gross.
That's nasty.
Yeah. Okay. So, you have two options here. I say on here, don't memorize this. If you are of the mindset that you can remember these things and can see how this could get rearranged to solve for density or molar mass, then great. If you're not, if that's not your strong suit, then just remember this equation. Unfortunately, it is not on your equation sheet. But you can remember dirty P, right? Ew. Knowing that, ladies and gentlemen, solve these problems. Go. What is the formula for ammonia? NH what? 3. Thank you. NH3. Okay, well, let's talk about what the units would be, okay? When you have a density, units for density are always units of mass per some unit of volume, okay? Well, remembering that this came from the ideal gas law, what do you think the units are here? Grams per what? Liter. Now, I want to say something about number 2. Do not get freaked out by seeing these words empirical and molecular. You're not going to have to work through all those steps, mass pull, none of that. Okay? I've given you the empirical formula right here. You are being asked to find the molecular. Folks, what do you need to get from an empirical to a molecular formula? Molar mass. So that's what you're solving for here. The molar mass. All of that information in the problem, the mass, the volume, the temperature, the pressure, that all related to the molecular formula. Okay? I was able to find the molar mass, and remember, you're going to see this combination a lot. Anytime a problem gives you an empirical formula and asks you for the molecular, what they're really asking you to find is the molar mass, which I did. If this is the molar mass of my empirical, 1 carbon, 1 hydrogen, 1 chlorine, it doesn't match, but you may have been able to see just by eyeballing it that this mass is half of that. So here is my molecular formula. All right. I want you to imagine that I have a balloon, and you know how much I love balloons. Okay. Folks, everything we've done so far relating to gases, there has only been one gas. If you have more than one gas, 2, 3, 4, 5, 50, if you have more than one, you have to think about what are called partial pressures. So let's say, for example, I have a balloon, and it does not just have one gas in it, it has 3 gases in it. Well, each individual gas has its own what's called partial pressure. Okay, and they don't have to be equal. I mean, this could be 1.2 atmospheres, this could be 0.8, and this is 0.1. Each one has its own partial pressure. If you add them all together, no matter how many there are, that'll give you the total pressure in that container, balloon, whatever. If, however, you are asked specifically about one of those gases within a mixture, you may have to use this equation, which is on your equation sheet, by the way. Okay? This would be the total pressure. Let's use the balloon. The total pressure of the balloon. This would be the partial pressure of the one gas that you're concerned with. And this x, that's the variable for what is called a mole fraction. Well, a fraction is just like any other fraction. It's a part over a whole. Moles of gas that I'm concerned with over the total moles in that container. Now, this word is misleading because let's say that you were given a problem, and we're going to do this in just a second, where you're asked to solve for x. Do not give me an answer that looks like this. No. I realize the word fraction is there, people, but we don't do fractions in chemistry. Never, ever. Fractions are for math. We don't do that in here. If you're asked to solve for a mole fraction, you need to divide this out. Give me a decimal. And by the way, what would the units be for the mole fraction? What's another way to say moles over moles? No units. There are no units. It's a unitless entity. So, knowing what you do, go. These are quick, very quick. And number 2 does pull information from number 1. They are related. They are connected. And by the way, your units of pressure do not matter as long as they are all the same unit of pressure. And I didn't make these numbers up, by the way. Okay? The air we are breathing right now is basically 79% nitrogen. I don't know if you knew that. Your dominant gas is not oxygen, it is nitrogen. Okay, folks, in your problem set for Chapter 5, you're going to have a problem that looks very similar to this one, and I will tell you that the AP exam loves gas law problems with these diagrams like this. They love it. So let me just explain to you what we're looking at here. We have one container that has 3 separate compartments. They're containing 3 different gases at 3 different volumes. They each have their own partial pressure. The X's represent valves, which right now are closed. So right now, each individual gas has its own compartment. Now let's look at the question. When these valves are opened, stop right there. Tell me what's going to happen here. They're going to mix. You don't have to do anything. You don't have to stir it. Gases spontaneously mix. And not only that, this is a really important part to solving this problem. Every single gas, all 3 gases, will expand to fill the entire volume. And it tells us down here, assume the final volume is 9 liters. That's just those 3 volumes put together. You are asked to find, once the valves are opened, what is the partial pressure for each gas, and what is the total. I'm going to give you a hint. This is the last thing we're doing today. Your hint is that you have to use Boyle's law to solve this. Go and look up what Boyle's law is. See if you can figure it out. How do you get the total pressure?
Add them all up.
Very nice.
We're smart. We're say add them.
Add them up.
You do chocolate chip on top.
Guys, there's just one more thing I want to say about this because somebody in my first period asked this and I thought it was a good question. She asked the question, each of the three individual gases, if you added the three original pressures together, why don't they equal the total pressure at the end? Shouldn't they equal the same? No, they shouldn't, okay? And I think what she was thinking about is like in a reaction, we have conservation of mass. Later in the year, we'll see conservation of energy. There is no such thing as conservation of pressure. Even though we haven't changed the amounts of gases, all we've done is change where they are. The pressure does not have to be the same before and after. I thought that was a good question. Okay? So, that's it.